Welcome back to the lecture series of microprocessors and microcontrollers subject. In our today's lecture, we will be seeing addressing modes of 8086 assembly language programming. In today's lecture, as I said, we will be talking about the addressing modes of 8086. Majorly, in general, there are three different addressing modes available in the assembly language. That is, either you just write your data into the instruction itself. That addressing mode is called as immediate addressing mode. In other two addressing modes other than this immediate addressing mode, it is a direct addressing and indirect addressing. In the direct addressing, we'll be having a location of the data given inside the instruction, that wherever the data is there, from that location it can be accessed easily. So directly the location of the data will be accessible in the instruction. That is a direct addressing mode. Okay. Earlier, I have told you about the immediate addressing mode, where the data itself it is available in the instruction. The direct addressing mode, the location of the data is given in the particular instruction, so such that the data can be directly accessed from that location. One more addressing mode is there. It is indirect addressing mode. In this type of addressing modes, indirect type of addressing modes, not the data, but not the location, but something else is given as a reference to the data in the instruction. Okay, so there will be something given in the instruction which will point to the data's location. From that location you can access the data. You can understand this by analogy that somebody may call you by your name directly, okay, and sometimes they may call you by your roll number, right? So direct addressing mode is calling you by your name, and indirect addressing mode is calling you by your roll number, because your roll number is associated with your name. And immediate addressing mode is calling you directly without taking your name, without taking your roll number, as if you are available there itself. Okay, hope you understand this analogy. Immediate addressing mode is calling you directly as you are available in front of the person, and other two are the direct addressing mode will be calling you by your name, and the indirect addressing mode is calling you by your roll number, whereas your roll number is associated with your name and your name is associated with you. So basically the addressing mode is tells us about that how the data is called into the program. You might have studied in your C language, there are two ways of calling data into the program, that is call by its value and call by reference. So there in C language it is very simple, only two type of calling is there, directly just call by the value or call by some reference. But here in assembly language of 8086 we have all sort of different options available for the call by reference thing. Your call by value is similar to the immediate addressing mode, but call by reference thing, we have all set of different ways in which the reference can be defined. The reference can be the person's name, for an analogy of the person human being calling I am telling you. Otherwise in data sense it can be, the reference could be the data's location address, the location into the register, or sometimes the address will be there in the register, so that register's access will be there in the instruction. So from register location will be accessed, from location data will be accessed. So and many ways are there. One by one, each one of that one we will be checking out in our today's class. So for make you understand the group 2, again I want to just tell you about this particular thing, that in 8086 the physical address is always calculated by adding two contents, two things. One is the offset address and another thing is segment address shifted by 4 binary bits or 1 hexadecimal digit, because 1 hexadecimal digit is equivalent to 4 binary bits. So shifting the segment address by 4 binary bits and then adding that result with the offset value, will get the physical address 20 bits. Now this offset number here 16 bit for the group 2 addressing can be referred in different ways. As I told you, it can be given as a directly a 16 bit number. Otherwise that 16 bit number can be split into parts, and its parts can be stored in BX register, BP register, SI register, DI register, and sometimes it can be written directly as a displacement number. So that is why there is one new term where you will be checking out from our next slide onwards, that effective address, EA, effective address. So basically effective address is offset address only when it is available at a standalone 16-bit number. But effective address will be the addition of the content of base registers, index registers and displacement if it is not available as a standalone, but it is split and stored into the different registers as BX, BP, SI, DI and sometimes a displacement number. We'll see with the examples also, not to worry about how this particular effective address is being calculated. Okay, anyhow, this slide again talks about that thing, the physical address calculation, which we have earlier seen also. Here we have to just wait and understand for the effective address how it being calculated into it. So this particular table, if you remember, you have seen while talking about the instruction formats. This table will be important for here also for us to understand the different ways the memory data can be accessed. As I said, the memory data can be accessed by writing its offset address directly. That is this particular thing here, 16-bit. D16 means 16-bit address, offset address of data has been written here in this case. And all the other cases, it is either written only in this BX register, you can check it, okay, or only in the DI register or only in the SI register, and sometimes else it is written, the part of it is in BX register, okay, and the part of that one is in SI register, okay. In this particular case, it is in SI alone, it is in DI alone, it is a direct 16-bit number, it is in BX alone. And in this particular case here, you can check it, the part of that address is there in BX, another part of that address is there in SI, and another part of that address is available as a 1 byte displacement, 8-bit displacement. So this table, you have to understand that this table talks about all the different sort of addressing modes, okay, all the different sort of addressing modes under the group 2. In the group 2 addressing modes, here the operand, the source operand is available as a memory data. So in all these 6 different types of addressing modes under this group, we have to understand that our operand number 2, that is source operand, is available as a memory data. That means it is the data located in memory, and that memory address is being indicated into the instruction of our use. Okay. In this group, the first type of addressing mode is the direct addressing mode. In the direct addressing mode, in the example, you can check it out here, that move dx comma a number in the square brackets is written. So anytime any number, when it is written under the square brackets, that particular thing they will be considered as an address. So here in this particular instruction, move dx comma this 1 to 1354h. In this particular thing, 1354h is actually a effective address or offset address of the data where it is located in the memory. So while executing this particular instruction, move bx comma this in the brackets 1354h, the data located at the address 1354h will be taken into the register given there. Okay, similar is the case in the next instruction example, move bl comma in the brackets 0400h. So in this case also 8-bit data from that location will be taken into this 8-bit register BL. In the earlier instruction, as the destination operand size is of 2 bytes, 2 consecutive bytes from this address, that means the offset address 1354 and 1355. These 2 addresses contained data will be moved into this register given here. Okay, so let us talk about our next addressing mode under this group. Next addressing mode here, it is a register indirect addressing mode. It is similar to the direct addressing mode what we have checked, but a little bit different in a way that here in the instruction, not the address is written, but one register is written. So we are expecting that what this BX will contain is a number which will be actually a memory address of our data. So move CX comma in the square brackets BX when it is written, we are expecting that BX is having one particular number in it. That number is actually a memory address of our data to be moved into CX register. Okay, here the operation what it goes on, it explains here that effective address is available in the BX register, and obviously the address calculation of the base will be the segment address multiplied by 16 decimal, or shifting that in the hexadecimal digits by one space to the left side, introducing one extra hexadecimal digit there. Okay, and a memory address, which we generally are calling physical address of the data here, will be calculated as adding this base with this effective address. So base from where we are getting the base address from the segment multiplied with the 10 hexadecimal or 16 decimal. Okay, so from there the memory address will be accessed, the physical memory address, and from there that physical memory address, whatever the data is there, will be moved into the CX register. Obviously in the memory locations, each memory location contains only 1 byte of data, but whereas the destination here, it is the 2 bytes. So what happens here is, you can see the memory address data, that is 1 byte, will be moved into CL register, and the next memory address, the subsequent memory address, that is memory address plus 1, from there the 1 byte data will be moved into CH register. Here our next addressing mode, right, third into this group 2, is base addressing. So here again it is more similar to the just previous addressing mode, that is register indirect. So here it is also a register indirect, but the only difference here is that the register in use, it is your BX register. Okay, so whenever your register indirect type of addressing contains a register of use, either the BX or BP register, that means the base registers, either BX or BP. So that sort of addressing, we call that one as a based addressing. So here we have to understand that effective address of our data lies inside the base register. So that base register here, it is BX, so it can be BX or BP. And the operation for calculating the effective address and then the memory address for the data access is being explained here as usual. Next is our indexed addressing mode. As earlier also the base addressing mode was there, in the indexed addressing mode also the operation of calculating the effective address will be the same. The only difference from what it is from the base addressing mode is that in the base addressing mode, either BX or BP registers will be containing the effective address, but in this indexed addressing mode we'll be having either SI or a DI register which contains the effective address of our data. Here next thing is based indexed addressing mode. So here you can say it's a combination of the earlier two addressing modes, the based addressing mode and indexed addressing mode. In the based addressing mode, our effective address was available in the base register, that is BX or BP. In indexed addressing mode, our effective address was available in the index register, that is SI or DI. In the base indexed addressing mode, our effective address will be available and actually computed by adding the contents of the base registers and the segment registers. So here at this place, the BX, you can have either the BX or BP. At the place of SI, you can have a SI or DI. So all such combinations of BX, SI, BP, DI, so will be giving us the base index addressing mode. In these cases, the effective address of the data will be calculated by taking the content of BX and taking the content of SI, adding them. When we add them, we'll get the effective address. And effective address, obviously, it's similar to your offset address of the data, as earlier we used to term that one. Next is relative based index addressing mode. It is again similar to the just before addressing mode than what we have discussed, that is based index addressing mode. One additional term or the quantity is added into this instruction, which is used for calculating the effective address. In the relative based index addressing mode, the effective address of the data is computed by adding the content of base registers plus the index registers and the displacement number. Displacement number again here can be a 8-bit displacement number or a 16-bit displacement number. As earlier in that table also we have seen, we have the BX plus SI plus D8 or D16, that means displacement 8-bit or a displacement 16-bit. So this particular addressing mode is called as relative based index addressing mode. Basically it is a based index addressing mode only with an relative displacement number indicated along with the base and index registers here. So the effective address is calculated by adding the content of base register and the content of index register and this displacement number. String addressing. This is a group 3 type of addressing out of our total 6 groups. In this group 3 addressing, specifically it talks about the string manipulation instructions. So this addressing is more specific to the string manipulation instructions only. Here most of these instructions are implied in nature. When I say implied in nature, here the meaning is that here you can find one of the examples of the string manipulation instruction, that is move SB. So here you are writing move a string byte from where to where you are not writing, because we are expecting that as an implied addresses for all the string manipulation operations. So for basically the string operations, effective address of your source string will be calculated with the help of our SI pointer, and effective address of the destination string will be calculated by pointing the and it is actually pointed by the effective address of the destination string is pointed by our DI register, and obviously the segment register is used for calculating the memory address of the source data and the memory address of the destination data. Here the data is a string characters actually. So for the segment register used for calculating our source strings base address, and the destination strings base address are our DS register is used for calculating the base address of the source string, and ES will be used for calculating the base address of our destination string. Okay, there are dedicated instructions available in 8086 instruction set which are specific to the string operations. So one example of that is move SB. Move SB is a short form notation for move string byte. Okay, a few more examples I'll just give you now, but you can later we will be discussing in detail. They are load SB, store SB, compare SB. That means load SB is LOD SB. Okay, store SB is STO SB, and compare string byte is CMP SB, and a few more are there. In detail, we will talk about the instructions used for string manipulations in our next class, where we will be talking about instruction set of 8086. So basically how to understand here is that effective address of the source string is there in SI register, and effective address of destination string is there in the DI register. So string source strings characters will be pointed by the SI register, and destination strings characters will be pointed by the DI register. Okay, and here it is how the memory source locations and destination locations will be calculated. For source effective address, you can see it is in SI. Base address, it is there in DS multiplied by 10, and memory address is calculated by adding the base address plus the effective address of the source thing. And when it is written EA suffix D, so that D is the data segment there. Okay, because data segment is the source and extra segment is the destination. So in this example here, calculation of the destination memory address or destination memory location is given by the EA suffix E. Okay, here that E means extra segment of memory. So effective address from the extra segment, it is there in the DI register. Base address is obviously the ES multiplied by 10 hexadecimal, and memory address is calculated by adding this two quantities, a 20-bit memory address or physical address, we call that one. And one important thing about the directional flag, what we studied while talking about the flags of 8086, DF is very important in the string manipulations, because here it decides whether the flow or the implications in the string instructions will be auto incrementing or auto decrementing. Suppose I say that I am writing move SB, I have a source string of 5 characters, it has to be moved to some destination. So move SB I will be using. So when it is moving, it has to progress for storing the, or actually it has to progress for moving our string characters from the first character to the last character, or the last character first then down to the first character. Okay, we will see the exact use of the direction flag here, but by default when the direction flag is 0, we say that the operations of the string manipulation instructions will be auto incrementing. That means you will be starting with your first character first. for moving that one to the other place. In this case of move example. And when the direction flag is 1, it will be doing auto decrementing operations. So that time, suppose you are just taking the last character to be moved first to the destination side, and even obviously the auto decrementing is both the source and destination locations will be decremented after every iteration of that execution of string manipulation instruction. We shall see this understanding by writing some program towards the end of this unit. Here it is our group 4. In group 3 only one addressing mode was there, that is string addressing. In group 4 we have addressing modes for IO ports. Okay, for all the IO operations there is a dedicated group of addressing modes here. Basically there are two particular instructions in this IO operations which is involved, that is in is taking the data input from the input sources, input ports, and out is the instruction used for sending the data out to the given output port. So these two instructions in and out will be there used for the input output operations. And here addressing, again there are two types in this, that is direct port addressing it is there, indirect port addressing is there. Obviously again direct port addressing is a one in which that the port address directly it is available as a address location inside the instruction itself. And in the indirect addressing port addressing mode, you will find that not the location of the port, but instead some register will be indicated in the particular given instruction. That register actually contains the location address of that particular port, or port address we can call that one. So we can write another example of in instructions in the indirect addressing mode as, suppose I write in AL comma in the square brackets DX register. So there I will be telling that DX register contains my input port from where the data has to be moved into AL. Whereas in this particular given instruction here, directly the address of that port is indicated in the instruction itself. So this is the direct port addressing mode, and here is the example of indirect port addressing mode, where the address of the port is not available as direct number in the instruction. Instead it is available in the form of one register. So prior to this we have to store that port address into the DX, such that word information can be sent out to that port from this particular instruction. And here next our group 5 is the relative addressing. In this only the relative address will be given, and most of the instructions using this type of addressing will be all the conditional jump instructions. Conditional jump instructions are one in which the execution flow of the program will be conditionally skipped at the other location. Okay, and that can be done, as I said, by the conditional jump instructions. The very good example of that one is a jump if 0. So this particular instruction will execute and make the processor execution flow to jump to the given location given here if suppose a 0 flag is set. Okay, so jump if 0. Okay, jump if 0 means if the 0 flag is set. So this instruction, when it is executed, the program execution flow will jump to this particular displacement here. This displacement will be positive or negative. It's a signed displacement number there, and the signed displacement number tells that from that point of the execution 0AH, as it is a positive number here, 10 locations ahead it has to jump. Okay, if it is a negative indication there, according to what negative number it is there, that many locations back into the program it has to jump. Basically in the program itself, conditional flow, conditional jump from the execution flow will be there. Conditional jump from the execution flow will be there. So in the relative addressing, we will write the relative distance from this location, this instructions location to the another instructions location where we expect our program execution to go. Okay, so here you can see that how operation carries out here is that first that 0AH is extended, signed extended, as the offset address or effective address will be 16 bits in format, but the 0AH when I am writing it, that is only a 8-bit number. Okay, if I ignore that 0, it's again just A, so 4-bit number only. So it is signed extended to make it look as a 16-bit number. Okay, 000 A. So this is the 16-bit effective address where the program execution has to jump from that particular location. And when it jumps, whenever the 0 flag is set. So if the 0 flag is 1, then the effective address will be calculated as the current status in the IP register, because IP register always stores the effective address of the next instruction to be executed. So that plus this displacement number will be the new value available in our IP register. So IP register will change the address of what has to be executed next. So it will just actually saying that jump to 10 locations ahead. A is the hexadecimal representation for 10 decimal. So 10 locations ahead it will jump by updating its value by 10 decimal ahead. Okay, base address is as usual calculated, memory address will be as usually calculated. And one other important thing about this instruction is that this instruction will be executed and the jump will be carrying on only if the 0 flag is set, or else otherwise the execution of this particular instruction will not make any difference in the program flow. It will continue executing downwards. We come to our last group and the last particular addressing mode, implied addressing mode. This particular example already 2 times we have discussed that here in this the opcode itself is self-sufficient to tell the processor what operation has to be done and upon what operand it has to perform that operation. So CLCE or CLI is very good example of this particular instruction, where we are clearing our carry flag by this particular instruction, or other one earlier I showed you that CLI, clear the interrupt flag. Here it is clearing the carry flag. Okay, so what operation has to be done and upon what operand it has to perform that operation, both are available in single byte format. So CLI, CLC, STI, STC, these are all the examples of the implied addressing. So that's it for today's session. Thank you. See you in the next session.